And what you're doing in this reaction is you're starting off with some type of an aldehyde or ketone, that's the basis of this entire chapter. We're going to run this reaction with a primary amine. So I'm going to go ahead and draw it like this. NH2 with an R group attached to it. I know that that's kind of goofy looking, but anyways, I run these two reactants here, sorry, and again, existing in equilibrium, just like with the previous one, under mildly acidic conditions. What I get out of this is a unique, I guess, kind of species known as an imine. So I'm going to go ahead and draw that. And we've talked about imines before. I don't think we've talked about them in this context, but it's basically where you have a carbon-carbon double bond to a nitrogen. And attached to that nitrogen is the R group, or the carbon group from whatever species you have. So this is called a imine. So that's my generalized overview. Let's draw out a stepwise mechanism for it. I've been trying to understand this, I guess, from a pedagogical perspective, but for whatever reason, under mildly acidic conditions, we don't have a proton transfer reaction here immediately protonating it. I'm just going to say for the purposes of this that a primary amine or secondary amine is a strong enough nucleophile that it doesn't need to have protonation happening first, for whatever reason that may be. And so the primary amine acting as a nucleophile, moving these electrons to the negatively charged oxygen here, and in doing so forms a positive charge. Notice that the charge has not, overall charge has not changed. But what's interesting about this is the next step, and there's two ways you can think about it. You can think of it as just protonating here and then deprotonating here, but I'm just going to go ahead and draw it as an intramolecular proton transfer reaction, and try to visualize this as a three-dimensional molecule. I suppose I could have rotated the positions of this NHR group to where that R group is, but this is a three-dimensional molecule, and we can have an intramolecular proton transfer reaction that is going to stabilize our molecule. And once again, my textbook has kind of, I guess, eluded me in that labeling this is known as a carbenolamine, but this is our intermediate, and for some reason it's considered unstable. It's unstable. What I don't understand is, well, comparing it to this guy over here, it's quite unique there. I don't see a reason why this would be, if it's so unstable. But anyways, it's considered, I guess, unstable in the grand scheme of things, even though it's a reaction that proceeds towards more stable equilibrium. And just like with all the other ones that we had talking about, we're running this in a mildly acidic conditions. We have lone pairs on this oxygen here, and we're running this under, mildly acidic conditions. I'm going to just go ahead and draw this as a hydronium species here, OH2. That hydronium is going to give off one of its protons, thus putting a positive formal charge on oxygen. And even though we have water existing from this that could just as easily pluck this off, or you could even think of it as visualizing this. This is an equilibrating reaction, and the lone pairs on the nitrogen are going to come in and apply themselves to carbon. Now, carbon cannot go over his octet rule. Sometimes he can go under, but he can't go over. And so what we're going to have is water, again, a leaving group leaving over a tertiary carbon, which is nice. So even though we have stabilized or made carbon having a happy octet rule, we went ahead and created, just like we had before here, a positive formal charge on the nitrogen. It doesn't want to be in the state long. We just formed water here, or you could think of it as any type of a generic base. Obviously, if we're running this reaction in water under mildly acidic conditions, that's what you're going to have here. So I'm just going to go ahead and draw it as water itself is going to see that, say, there's a proton there, and I can take it away, just like with every other type of reaction that we've drawn. This obviously reacts to give us our final product of our imine, and then we can say that we're done, at least in terms of this reaction. So this is what happens if we're running this reaction under mildly acidic conditions at a pH of about, I believe it says 4 or 5. So what kind of a pH is this reaction running in? At about a 4 to 5, which is not superbly acidic. But what if we ran this reaction, the same addition reaction that we talked about of primary amines, with a basic pH? What do you think would happen there? Well, what I think is interesting, at least worth noting, is that the protonation reaction gives us a very good leaving group, but if we had a low pH, we would have no reaction taking place, because our starting material, our primary amine, which I'll just go ahead and draw that out here, hydrogen, hydrogen, R. Those lone pairs are what make it a good leaving group. I'm sorry, a good nucleophile. Not a good leaving group, it's a good nucleophile. I'm losing my edge. But if we run this under low pHs where it's incredibly alkalotic, well, what does Le Chatelier's principle tell you? That reaction is going to proceed towards equilibrium. This is a base. We're going to want to react with whatever we can get to give ourselves a more milder species. So even then, if we have this reacting in hydronium ions, which will be formed even under low pH conditions because of the acid-base reactions of water, we're going to end up protonating your primary amine, forming a non-nucleophilic species. So what we get out of this, I wonder if this is an equilibrating reaction. I don't know. If I wanted to know, I would look up the pKa values to see. But this is why it has to be run under acidic conditions and not basic conditions. All right, so now let's talk about addition of secondary amines. And so just like with before, we start off with some type of a aldehyde or ketone, doesn't really matter. But I will say this, that the next secondary R species cannot be a tertiary species. It has to be at least a secondary species, and I'll explain why I'm talking about that later. And then we go ahead and treat this with a secondary amine, which is something that has just a hydrogen, an N, and two R groups attached to it. I don't know how well you can see that, but I go ahead and I'm just going to write it in the substituted form of HNR2. And what I get out of this reaction, I don't know if I can fit it in here, I'll try to see if I can squeeze it down up there, is something called an enamine. And I'll clarify what I'm talking about here in a sec. So we have a carbon there, we have a R group there, we have a double bonded here, 2RN, R2, there's my compound there, and there. So the product that we're forming out of this, I don't know if you can, it's kind of cramped, is called an enamine, and this is kind of interesting because it's followed by two words. It's part alkene, and then the other part of it is an amine. So that's why it's called that. Cool. Let's draw the overall, or the stepwise mechanism of this reaction. So just like before, we have ourselves a secondary amine. We're going to run this under acidic conditions so that this reaction does not, or so this nucleophile will react as a nucleophile and not as a base. And so we end up getting a nucleophilic attack of the carbonyl carbon. For the purposes of convenience, I went ahead and moved this. This is obviously is a trigonal, not a trigonal, this is a tetrahedral molecule. It's can be rotating in either form, so I'm just keeping that in mind that this is a three-dimensional, not a two-dimensional molecule. But just like before, we have a proton transfer reaction taking place here to satisfy that negative and positive charges. It's kind of messy, I don't know how much that can see, but it'll make sense when I draw the products of this reaction. So just like before, this is the same species that we talked about. It's a carbonyl amine, and it is our reaction intermediate. It's considered unstable despite the fact that it's, yeah. Anyways, moving on to what we were discussing here, this is under mildly acidic conditions, and it's obviously in the presence of acids. So there's my hydronium there. I have lone pairs on this oxygen, and I'm going to get a protonation reaction. So just like before when we had talked about this, we now have a positively charged oxonium ion that doesn't want to be in that state. We go ahead and move the electrons down there because they're attracted to that, and carbon can't go over his octet rule, and we have a water leaving our molecule. So just like before, when we talked about primary amine additions, whenever we got to this step, we have our positive charge here. There is a proton that we could pluck off that would leave behind some electrons that we could use to stabilize everything. But now we don't have that luxury because this is all R groups. There's nothing that we can react with. So the next step is really kind of the I guess, differentiating step between the two species. And I've drawn this hydrogen here, and I said that, you know, you can't have a tertiary carbon on both of your R groups. And this is why, because what happens after this, and this is kind of, I want to say frustrating to see this, because it says that, this is from my textbook at least, that water acts as a base to pluck a proton off of an sp3 hybridized carbon. Mechanistically, I hate to see that, but nevertheless, that's what we have. For forming this pi bond here, we have all in one step, essentially, as you know, think of it as passing around here, the electrons from the pi bond in the imine type of a bond structure there move back to being placed on the nitrogen, and that's going to give us our final product. So voila, you have now formed your enamine, and obviously your hydronium ion catalyst that you had was also formed from this transfer here. And that's pretty much it for that. So while I really generally hate shortcuts, and I hate understanding this, if you're pressed for time, this is something that I think you should keep in mind. But always be comfortable drawing the reaction in reverse, and if you know the way the reaction works, you just draw it backwards and you understand how hydrolysis works. But for both hydrolysis of an imine and an enamine, if just say that you're pressed for time, I want you to just note that any time you have a carbon-nitrogen bond, so just note that any carbon-nitrogen bond will be cleaved to form our aldehyde species, and then whatever type of amines, primary or secondary. And that's only if you're pressed for time. But be comfortable drawing these reactions in forward and reverse.